back. Today we're going to continue our exploration of hypothesis testing of multiple samples and focus in particular on the test of equality of variances of two or possibly more populations. We've actually already discussed how to conduct this test with pairwise comparison test, but we do know that pairwise comparison tests come with the downside that you could be performing a type 1 or type 2 error for each pairwise comparison test they were actually executing for this multiple population equality test. So what I'm going to do today is focus on the homoscedasticity test for two or more populations and introduce three different tests that actually focus on this, but each of these three tests actually assume slightly different things, and those are known as the Bartlett, Levene, and Brown-Forsythe test. So of course you need to figure out, okay, we're going to have K populations here, so what do I need from them in order to conduct a Bartlett, Levene, or Brown-Forsythe test, or possibly all three of them. So the first thing that we need to do is collect a simple random sample from each of the K populations. So each of the K populations. And for each of those populations, and let's assume that they're called, for example, sample J, those sample J's, this is the information that you need from them. So the first thing that you need is, of course, the sample size. And of course, the samples from each of the populations don't have to be the same size. But of course, there is some theoretical advantages towards those when you do have equal sample sizes, but we'll discuss those very special things a little bit later. Another thing that you will need, for example, for the Bartlett test is you need the sample standard deviations or the sample variances, i.e. Sj squared. For the Levene test, you need to also take and calculate the arithmetic mean of those samples. And if you want to do a Brown-Forsythe test, you also need to calculate the median of each of those samples. So one sample size, one sample median, and one sample standard deviation or variance. And here J ranges from 1, 2, 3, all the way down to the number of samples that you are collecting. Right, so if you want to conduct a Bartlett, Levene, and Brown-Forsythe, calculate a sample size, mean, median, and standard deviation, and you'll be able to do all three. So let's start off with the most straightforward one, and that's going to be the Bartlett, or the Bartlett's test for homoscedasticity for two or more populations. So one of the requirements for the Bartlett test is that it requires, and this is actually where Bartlett differentiates from Levene and Brown-Forsythe, is that it mandates that the population J is associated to a normal distribution with some mean mu and some variance sigma squared, where of course mu and sigma are unknown to us, because if we knew all the variances, then we could test whether they are directly equal to one another or not. And that's of course for J is equal to 1, 2, down to K. So, if you do not have all of the populations that you're sampling from normally distributed, then the Bartlett test will not be appropriate, and you would have to use, for example, a Levene, a Brown-Forsythe, or what is known as a non-parametric test that assumes absolutely nothing about the distribution that we're sampling from. But let's at least assume that we are sampling from a normal distribution, and you could, of course, test each of those samples, for example, with a normal quanta-quanta plot to make sure that all the samples appear to be coming from a normally distributed population, right? So this is ideal for situations, or let's assume the ideal case where we want to, for example, fail to reject the null hypothesis, where the null hypothesis is that sigma 1 squared and sigma 2 squared all the way down to sigma k squared are all equal to each other. So the ideal scenario, once we do calculate all of these samples, is that all of the sample variances are equal to each other. So s1 squared, s2 squared is all the way down to, for example, sk squared. So if all of the sample variances are equal to each other, regardless if you're using Bartlett, Levene, or Brown-Forsythe, that's probably going to be the most optimal test statistic that you could use for your particular population. So let's just keep this optimal scenario in the back of our minds just for now, and we'll discuss sort of how this plays into the test statistics that we're going to be talking about and using, for example, for the Bartlett test. Right. So now we're going to define what is called the pooled variance. So the pooled sample variance. So the pooled sample variance, which is going to be represented by SP squared. So SP squared is going to be the sample variance. This is going to be defined to be equal to nu1 S1 squared plus nu2 S2 squared all the way down to nu k SK squared all divided by nu1 plus nu2 all the way down to nu k, where nu j corresponds to the degrees of freedom, so the sample size minus 1 for each of those particular samples. So a couple little simplifications one can do with this particular formula. So if we denote, for example, if n is equal to n1 plus n2 all the way down to nk, and we can also denote nu to be equal to nu1 plus nu2 all the way down to nu k, then you can actually rewrite nu1 plus nu2 plus down to nu k, the bottom of this denominator just precisely as, for example, nu, and you can also represent some other things as well, which we'll define momentarily. So v, you should also be able to prove that v is actually equal to n minus k. Now why is that the case? Because this is, keep in mind, n1 minus 1 plus n2 minus 1 plus down to nu k minus 1. So how many minus 1s do we have? We have k of them. So it's n1 plus n2 plus n3 down to nk minus k, which is just the same as n minus k. So v and n minus k are equal in this notation. So we have an alternative representation for the pooled variance, and that's just going to be equal to 1 divided by the total degrees of freedom multiplied by the sum from j is equal to 1 to the number of samples that we've collected of nu j sj squared. So that actually is a more compact representation, which is more useful for like the R programming or Excel implementations of pooled variance. But keep in mind that is just the same thing or more compressed form of the formula that I just mentioned above. So now that we've defined the pooled variance in both its expanded and its compact form, now what I want to do is define what is called the Bartlett test statistic. So the Bartlett test statistic. The Bartlett test statistic. So the Bartlett test statistic, which I'm going to be abbreviating as B-stat, is going to be equal to, and this formula might come across as very intimidating at first, but we can step through it piece by piece. So we're first going to have V, which keep in mind is V1 plus V2 all the way out to Vk, that's the total degrees of freedom, times the natural logarithm of the pooled variance, and we already know how to find the pooled variance. And then we're going to subtract the sum from j is equal to 1 to k, the number of samples that we've collected, of the individual degrees of freedom times the natural log of the individual sample variances. Okay, so that's total degrees of freedom. That's the total pooled variance and the natural log of it. And here it's the individual degrees of freedom times the natural log of the individual variances. So V1 natural log of S1 squared plus V2 natural log S2 squared plus all the way down to VK natural log SK squared. And keep in mind there's a minus in front of that. So make sure you add them all up and then subtract that value from V ln SP squared. So that's the numerator of this Bartlett test statistic. And then on the bottom, we're going to have 1 minus a fraction, 1 divided by 3 times k minus 1. Again, k is the number of samples or populations that we're studying. So obviously, k should be greater than or equal to 2, else this doesn't really make much sense. And then we're going to be multiplying that by 1 divided by the total degrees of freedom minus the sum, again, from j is equal to 1 to k of the reciprocals of the degrees of freedom. So this little summation is 1 over nu1 plus 1 over nu2 plus 1 over nu3 all the way out to 1 over nu k. You add up all of those inverted degrees of freedom and then you subtract that from 1 over nu. Now, I'm not going to prove where this formula comes from, but if you know something about, for example, log likelihood, then we may be able to have a theoretical discussion of where this is coming from. But let's just define this as what it is, and this is what we call the Bartlett test statistic. And one may be able to show that this Bartlett test statistic is actually always greater than or equal to 0, regardless of the values of the degrees of freedom and the sample variances. Now, there's one important theoretical aspect that you definitely should be aware of. So, for example, if n1, n2, all the way down to nk are all equal to each other, and the variances s1 squared, s2 squared, all the way down to sk squared are all equal to each other, then the Bartlett test statistic will be equal to the minimum value for which the Bartlett test statistic can have, which is going to be 0. And since that is the ideal scenario for failing to reject the null hypothesis, then this Bartlett test statistic is the ideal one for failing to reject the null hypothesis. So this is ideal for failing to reject the null hypothesis of equality of variances, which means if we have a Bartlett test statistic that is equal to 0 or significantly close to 0, then we have evidence to believe that the populations are homoscedastic to one another. Okay? But generally speaking, this is not the case, right? Usually the sample sizes are going to be different and the variances are also going to be different as well, right? So one can probably guess what the distribution of this is going to look like, but nonetheless we know that the minimum of B stat is going to be is equal to 0, right? So of course there's going to be some unknown distribution associated to this particular curve, and we're not going to get into the theoretical aspects of that. But we know that if we have a B stat that is close to 0, then we have evidence to believe that they're homoscedastic to one another. But there's going to be a point somewhere out here that is going to be too far from 0 for us to believe that they are equal to each other. And that cutoff point is going to be referred to as the Bartlett critical value. So it's the same exact concept as, for example, T critical values, Z critical values, F critical values, and chi-square critical values. Same idea as before. So how far is far from 0? If our test statistic is larger than our critical value, then we're going to be rejecting the equality of variances, right? So this area is going to be our rejection region. So that's going to be our rejection region. So that means this shaded alpha area is going to correspond to alpha, right? So for example, if our B test statistic is greater than our B critical value, we're going to reject the null hypothesis that the variances sigma 1 squared, sigma 2 squared, all the way down to, for example, sigma k squared are equal to each other. That means at least two of these pairs of variances are significantly different from each other, causing all of them to be not equal to each other. Right? And of course, if B stat is less than the critical value, then we have evidence to believe that they are equal to each other, right? The closer to 0, the better in terms of failing to reject, right? Now, one can show, well, how do you find this B critical values? The distribution of this B test statistics and B critical values is approximately a chi-square distribution with k minus 1 degrees of freedom. Right, and we know the distribution of chi-square. We know the distribution of chi-squared is something along the lines of it, right? So how I drew my little purple curve is not, by chance, right? It will look something like this. So our Bartlett test statistic is going to be somewhere along this, right? So there's going to be a chi-square test statistic where this distribution is going to be a chi-square k minus 1 distribution. Right, so once you calculate the number of samples that you're collecting, you subtract that by 1. That's your degrees of freedom for chi-square distribution. And for example, this is going to be a one-tailed test. So for example, that alpha value probably is going to be like 5%, 10%, 1%, or whatever alpha value you're working with. That's going to allow you to get your Bartlett critical value. And then you can, for example, calculate, that should say chi-square crit there. And then once you have your chi-square critical value, then you can compare your Bartlett test statistic. Is it to the left or to the right of that? And that's going to allow you to fail to reject or reject that null hypothesis of homoscedasticity. Okay? So that is the theoretical aspects of the Bartlett test statistic. Let's get into a numerical example and see how we would go ahead and calculate these things. So let's assume that we're interested in testing whether the frog lanes in different water temperature cultures is homoscedastic to one another. So we're not testing whether the means in these different water temperature cultures are significantly different. We're just seeing if the variances amongst each of them are about equal to each other. Now, we're not going to test for normality here, but that's typically what you would do for the appropriateness of a Bartlett test. But of course, you can construct a normal quanta plot for each of these three samples and see if it looks approximately normal or not, and then you can decide whether the interpretations we have are appropriate or not. So let's assume we've collected a bunch of different frogs in these particular water temperature cultures, and we have these particular lengths, say in millimeters or centimeters or whatever unit, small frogs, big frogs, depending on, what world you're in. Okay, so once you have your data, and you can of course try to calculate these things, say in R or Excel or whatever software you're using, and sort of see if you can generate these numbers as well. So the first thing that you probably want to calculate, since we're going to be starting with a Bartlett test, is calculate the sample variances. So these sample variances, S1 squared, S2 squared, and S3 squared, since we're going to be using variances and not standard deviations directly in the calculations, one can find that that's going to be equal to approximately 0.99, 2.88, and 0.37. So those are the sample variances. So once you have your sample variances, you should be able to calculate the pooled variance for this particular data set. So one can find that for this particular data set, the pooled variance is going to be approximately equal to 1.31. Once you calculate the pooled variance using that formula from before, you should be able to calculate very carefully the Bartlett test statistic for that particular data set to be approximately equal to 6.33. Now, of course, 6.33 is greater than 0, but is it significantly greater than 0? Okay, so how are we going to compare that? So we need to construct a chi-square distribution. Keep in mind, since we're working with, for example, k is equal to 3, different populations for which we're analyzing, this is going to be a chi-squared 2 distribution, 3 minus 1. So what we need to do is find, for example, our Bartlett test statistic, which is going to be located somewhere along here. So let's assume that that is 6.33 in our picture. And instead of calculating, for example, the Bartlett critical value, you can actually just calculate the p-value associated with the chi-square distribution in the upper right-hand tail, right? So for example, if we're working in the integral realm, we can just do the integral from 6.33 to infinity of the chi-squared 2 distribution with respect to x, and that's going to give you, for example, the p-value, or you can just use R or Excel or whatever software you're working with to calculate the p-value. So the test statistic 6.33 associated to a chi-squared 2 distribution is going to give you a p-value of approximately 0.0422. So if you're working with, for example, with an alpha value of 5%, that's what some people work with, so let's just go ahead and go with that. So if alpha is equal to 0.05, then we have that the p-value is less than our alpha value, so that means we're going to be rejecting the null hypothesis that sigma 1 squared, sigma 2 squared, and sigma 3 squared are equal to each other. So that means at least one pair, either 1, 2, 1, 3, or 2, 3, is significantly far from one another, and you can look at the sample variances and probably figure out which one is super far from the rest. All right. Now, of course, since our p-value is 0.04 and our alpha value is 0.05, that does not mean, and it's far from meaningful, that this is significant evidence that they are different, right? Because 0.04 and 0.05 is just 1%, and nobody technically in the scientific community would accept that to be significant, right? Usually a p-value of like 0.000000001 would be okay, right? Because regardless of the alpha value you choose, that's going to be significantly small, typically, right? But keep in mind that's the downsides of p-values and critical values, and this is heavily dependent on the assumption that the populations are normal, which they probably or possibly aren't, right? So if that is the case, then we definitely have some issues. Now, let's talk about that case where the populations, one or more of them, are not normally distributed, which is going to sort of segue us into the Levene and Brown-Forsythe test. Right? So note, if you believe that P1 is not normal, or P2 is not normal, or all the way down to or PK is not normal. Any of them, right? One or more. If this is the case, then do not use the Bartlett test. Okay? Very, very important. So let's create a little flowchart here. So normal. Let's say all normal. If they are all normal, and the answer is yes, then Bartlett is appropriate. But if no, then we have to ask a couple questions. Is it almost normal? So that's, we have to create a threshold on close to normality. Maybe a correlation coefficient for the normal quantile plot will be sufficient there. But once you have a threshold, if the answer is yes, then you can use what is called the Levene test, right? And I'll go into discussion of what that test is. So if the answer is, of course, no, actually, let's draw our little arrow here. That flowchart looks a little strange, right? So if the answer is no, it's not almost normal. So is it sort of normal? Question mark. And let's draw a couple pictures, right? So what does normal mean? So normal means something like that, right? So what does almost normal mean? So maybe it's slightly skewed like that. What is sort of normal? Maybe a little bump there. It's sort of normal. It sort of has a unimodal distribution, but it sort of has, some weirdness associated to it. So if it's sort of normal, and the answer is yes, then Brown-Forsythe is going to be okay. And if the answer is no for that, then that means we have not at all normal. Sad face. Right? So not at all normal is like, something weird like that, right? So if that's the case, Bartlett, Levene, and Brown-Forsythe are all going to give you misleading results, and you probably need to use what is called a non-parametric test to solve that. And an example of a non-parametric test to test the homoscedasticity of multiple populations is called the signed ranks test, which we will discuss a little bit later once we start talking about parametric testing. But for now, we're just going to assume that our populations are either A, normal, B, almost normal, or C, sort of normal. That is, normality is sort of present in all of our populations, implying the appropriateness of Bartlett, Levene, or Brown-Forsythe. But keep in mind, if they're very far from normal, don't use any of them. You're going to get misleading results. So now that we know how to conduct a Bartlett test statistic and know when it is appropriate or not, let's do an example of both the Levene and the Brown-Forsythe test and sort of see how the calculations for the Levene test statistic and the Brown-Forsythe test statistic differ from the Bartlett test statistic. So keep in mind, for the Bartlett test, we only use the sample sizes and the sample variances. For the Levene's test, we're going to be using the sample means. So the very first thing that you want to calculate for the Levene's test is the grand mean of your data set, which can be viewed as a weighted mean for all of the samples under investigation. So in this calculation, it would be the sample size of 1 times the mean of 1, the sample size of 2 times the mean of 2, all the way down to the sample of the sample size of the last set times the mean of the last set divided by the total sample sizes. So if you want a more compressed form of the grand mean, you can write the grand mean, for example, keep in mind n1 plus n2 all the way down to nk was just equal to n. So we have 1 over n times the sum from j is equal to 1 to k of nj times x bar j. Right? So that is what we refer to as the grand mean. Now the next calculation, which I'm going to define as SSM. Now I'm not going to go into the detail of what SSM actually stands for because this actually ties very closely into a concept that is very deeply discussed once we start talking about multiple linear regression, which is going to stand for eventually the sum of squared differences for our model, right? But we're not going to get into the details of what SSM actually represents, but it's actually going to have the same exact formula later. So we're just going to define it as SSM now, since we don't want to introduce any more notation than what needs to be defined. So the SSM is going to be defined as the sum from j is equal to 1 to k of the sample size of a particular set times the arithmetic mean of that particular set minus the grand mean of all of your data, right? So that's going to be n1 times x bar 1 minus grand mean squared plus n2 times the squared difference between x bar 2 and x bar bar, all the way down to the squared difference between x bar k minus x bar bar times the sample size of that last particular thing. Once you calculate your SSM, then we're also going to define another quantity that's going to be thoroughly investigated later called the MSM, and the MSM is going to be defined to be equal to SSM divided by k minus 1. Now, even if you don't know what SSM and MSM stand for, if you know a little bit about random variable theory, that top, if we divide that by k minus 1, then you should know that this is going to be associated to a chi-squared k minus 1 distribution, assuming that the data is normally distributed. Now, since we're working in Levene's test, keep in mind we're assuming that the data sets are not linearly distributed, but keep in mind it has the same exact structure. So when we say it's approximately a chi-square distribution, keep in mind it's not really a chi-square distribution, right? But keep in mind this notation of SSM and MSM, we're going to get into what they stand for later, but we're just defining these as so. And also, if these data sets xj and x bar bar are normally distributed, then the quotient of SSM divided by k minus 1 will follow approximately a chi-square k minus 1 distribution. The farther these are from normal, the more far MSM is not going to be distributed according to a chi-square. All right. So once we have that, now we're going to define a third structure. So the third thing we're going to define is, well, you should know this from basic statistics maybe, so the difference score for a particular value is going to be equal to the value minus the sample mean, right? Where x belongs to a particular set and x bar the arithmetic mean of S. So that's the difference score, how far x is from the mean. And if we divide that by the standard deviation, that's going to give us our z-score. So from this, what we're going to do is we're going to define the absolute difference score to be equal to the absolute value of dx, or expandedly, the absolute value of x minus x bar. So this is referred to as the absolute difference score. Right? So how far x is from the mean. So from here, we're now going to define another quantity. So we're going to define SSEL. L is going to stand for Levene, because this is where the Levene and Brown-Forsythe are actually going to differentiate apart. And this is going to be the sum from j is equal to 1 to k of the sum from I is equal to 1 to the sample size of j of aij minus x bar j squared. Now, first question, what does SSC stand for? Again, the notation is going to be parallel to something we investigate later on when we start talking about regression. But for now, we're just going to call it SSE for Levene. Okay, so let's talk about what these little pieces are here. So for each element in each set, we're going to find the absolute score minus the mean of the group for which that particular element belongs. We're going to square that. We're going to add them all up, and then we're going to do that for every single group, right? So we're looking at the absolute difference score minus the mean for every element in the set, and then we're going to do that for all of the groups and add all of them up. So once we define this SSEL, we're then going to define an MSEL, which is going to be equal to SSEL divided by n minus k. Here, n is the total sample size, k is the particular number of groups, and again, if these values are approximately normally distributed, then this should be approximately a chi-squared n minus k, random variable, but keep in mind we're assuming that things are approximately not normal. So that means this is not really a chi-square distribution, but we're going to pretend it is, right? Which poses a downside for the Levene test, right? So the last thing we're going to define for the Levene test is finally the Levene test statistic. So the Levene test statistic. So the Levene test statistic, which we're going to abbreviate by LSTAT, is going to be equal to the MSM divided by the MSE subscript L. Right? So keep in mind, what do we have here? So we have a chi-squared distribution on top, not really, divided by a chi-squared random variable on the bottom. So if you remember, if you divide two chi-squared random variables, then you get what is called an F random variable, and the top degrees of freedom is going to be k minus 1, and the bottom degrees of freedom is going to be m minus k. Right? But again, if they're not really chi-squared random variables, it's not really a F random variable when you divide them, right? But as long as you don't deviate too far from normality for your data sets, then LSTAT is going to be approximately an F random variable, right? So that is the breakdown of the Levene test. Now let's go back to our data set and see how we would go about calculating all of these little intricate little measures. So we're going to be using the same exact data as before because we already calculated the Bartlett test statistic and got a conclusion. So it would be reasonable to use the same exact data and then compare our conclusions to the Levene and Brown-Forsythe test just to see if they are producing different results. So keep in mind the Levene and also Brown-Forsythe tests are not going to be calculating anything with variances. Everything is based on central tendencies, in particular the mean for Levene and the median and mean for Brown-Forsythe, which we'll discuss momentarily. So the very first thing that we need to calculate when we have some raw data is the arithmetic means of each of our samples. So you should be able to show that the arithmetic mean of 1, the mean of 2, and the arithmetic mean of 3 is going to be approximately equal to 15.03, 12.27, and 9.88 for our data set. Once you have your individual arithmetic means, you should be able to calculate the grand mean, which is just a weighted arithmetic mean for the entire dataset, to be approximately equal to 12.61. This is the very first thing you should be able to calculate. Once you have your grand mean and your individual means, then we can calculate our SSM. So keep in mind our SSM is going to be the sum from j is equal to 1 to 3 of our sample size n1, n2, n3 times the squared difference between x bar j and x bar bar, the quantity squared. So for example, if the first sample size was like 10, it would be 10 times 15.03 minus 12.61 squared. So subtract those two particular values, square them, and then multiply by the first sample size. And then do 12.27 minus 12.61 squared, multiply the second sample size. And lastly, you would do 9.88 minus 12.61, square it, and multiply it by the last sample size. Add those values up. That is your SSM. All right, and you should, for our data set, come out to approximately 119.21. So that's the first major part of the Levene calculation. Right. The next thing that we need to do is calculate our absolute differences, right? So it's probably easiest, especially if you're in R, to do everything in vectorized form. For example, if we do, for example, AJ, this is going to be equal to the absolute value of xj minus x bar j, right? So let's sort of think about what this is. So AJ corresponds to, for example, AJ1, AJ2, all the way down to, for example, AJ NJ. Right? So it's the absolute difference for each of the values located in sample J. Okay? So if we're thinking about these from the vector perspective, AJ and XJ are both vectors. Right? And X bar J, that is a number. And this subtraction is element-wise subtraction. The only reason I mention this from the vectorized perspective is because R, MATLAB, and all these languages, and sometimes Excel, if you approach it correctly, is all optimized towards vectorized manipulations, right? Which is why linear algebra is so important, especially when you start working with big and complex data. Okay, so once you calculate your vectors for each of your data sets, then we can calculate our SSEL. So our SSEL, our SSE Levene, if you want to call it that, is going to be the sum from j is equal to 1, 2, 3, since we have 3 groups, and then we're going to sum from I is equal to 1 to nj of aij minus x bar j, the quantity squared. And since this complication is a little bit complex, I would just want to list this out in slightly expanded form just to see what we're actually looking at here. So we're going to be adding up all of these sums, right? So what are all those sums? Let's actually look at them individually. So this is going to be the sum of a1 minus x bar 1 squared, right? So keep in mind a1 minus x bar 1 is a vector, and then we're going to element-wise square those values and then add up all the values in that resulting vector. And then we're going to do the same for 2, so the sum of a2 minus x bar 2, the quantity squared. So each of the values minus the mean, square those differences, add them up. And then we're going to do the same for the last one, for example the sum. All the absolute differences for the third group. And then you're going to take the mean and you're going to subtract that from each of them, square each of those differences. So keep in mind the absolute difference is a difference too, so technically a difference minus something else, right? Square them, add up those values, and then you're going to add these sums up, and that is going to give you SSEL, which is typically going to be a large number. So for our particular example, SSE subscript L, or SSE Levene, is going to be approximately equal to 3,559.52. Okay? So now we have our SSM and our SSE subgrill. Now we can calculate our MSM and our MSE Levene. So keep in mind the MSM is going to be equal to the SSM divided by k minus 1, so 3 minus 1 in our particular case. And that's going to come out to approximately 59.60. And then our MSE Levene is going to be equal to the SSE Levene divided by n minus k. And for our particular case, that's going to make that number super smaller than it used to be. So that's going to be 161.80. Once we have our MSM and our MSE Levene, then we can calculate our associated F-test statistic, assuming that it is appropriate, of course. So our F-test statistic is going to be approximately equal to, keep in mind, MSM divided by MSE Levene, and that's going to come out to approximately 0.3684, right? So once you have your F-test statistic, then we're going to be looking at our associated F distribution. Keep in mind this F distribution is going to be equal to a k minus 1 m minus k distribution, and you should be able to calculate what those numbers are for our example or your example. And then we're going to have our F-test statistic located here. And again, this is going to be a one-tailed test. So this area here is going to be our associated p-value. So for our particular example, once you calculate your k minus 1 m minus k and that p-value for that, you should be able to find that the p-value is going to be approximately equal to 0.3040. So if we choose the same exact alpha value as before, so if alpha is equal to 0.05, we have that the p-value is going to be greater than our alpha value. That means we're going to be failing to reject the null hypothesis that sigma 1 squared is equal to sigma 2 squared is equal to sigma 3 squared, which is a different conclusion compared to the Bartlett test statistic, right? So if that is the probability, or if that is the case where Bartlett and Levene give you different results, it's probably due to the fact that the distribution for one or more of these samples is not normally distributed. And that's probably one of the reasons why they are generating differences in terms of conclusions. As we discussed when we were going through the Levene test for homoscedasticity for more than two populations, we discussed that, for example, if these data sets are not all normally distributed, then this ratio, SSE Levene divided by m minus k, is not necessarily going to be approximately equal to a chi-square distribution. Same thing can be said about the MSMs as well, right? So why is that the case? Well, this approximation may be extremely harsh due to skewness, or some other things. If it's not even skewed, it could be completely not normal, right? So this approximation could be extremely bad. Now, if it is still approximately normal, keep in mind that there are other measures of central tendency that are a little bit more reliable than the arithmetic mean. So keep in mind, if our data set or our population is slightly skewed, but I'm just going to put skewed here just to keep it brief. So if P is skewed and the skewed is moderate, not extreme skew, but still resembles an approximate normal distribution, then the median for a particular data set is more reliable than X bar for that data set or for that associated sample. Right? And we've discussed why that is the case, because arithmetic means are more attracted to outliers compared to, for example, medians are, which sort of leans into why the median is more situated around most of the data compared to means for heavily skewed or even moderately skewed data sets, right? So what the Brown-Forsythe test does, right? So this is pretty much the segue into Brown-Forsythe. So Brown-Forsythe is that it tries to fix or tries to still use a chi-square distribution for that ratio by choosing a different measure of central tendency for these calculations. So the difference in the calculation between Levene and Brown-Forsythe is it uses this new term. So it defines AX star to be equal to the absolute value of a value minus the associated median of that set. So remember, the absolute difference between for a number is just the value minus the mean and its absolute value. So instead of comparing every value to the mean, we're going to be comparing every value to the median. So again, we're going to be writing this in vector form. That would be a vector, that would be a vector, that would be a number, and that would be element-wise subtraction. And then we can sort of approach this as before. So we're going to be, for example, defining a different SSE. So the SSE Brown-Forsythe is going to be equal to the sum from j is equal to 1 to k of the sum from I is equal to 1 to nj of aij star, so the median-based absolute difference minus x bar j. So we're still comparing those to the mean because there are analytical reasons why, which I won't get into. But since we've adjusted for the skewness with the median in the first one, some people will argue that it's still appropriate to use the mean in the overall comparisons. Okay. So once we have that structure, then you can define the MSE Brown-Forsythe to be equal to the SSE Brown-Forsythe divided by n minus k. And even if the MSE was not approximately chi-squared, this will be more approximately chi-squared than the other one would be. So this is going to be associated to a chi-square n minus k distribution, and of course this is going to be more reliable than the MSE Levene for small skewness. And again, you would have to have a threshold in order to identify whether it's small skewed or heavily skewed, like a skewness coefficient of less than plus or minus 5 or something like that. Okay. Now, notice I'm only defining SSEBF and MSEBF. I'm not talking about, for example, the SSM and MSM. That's the same as before. So the SSM and MSM are the same as Levene. That's why I didn't call it, for example, SSM Levene or SSM Levene, because it's actually the same for Levene and Brown-Forsythe. Okay, so now that we have our MSM and our MSE, now we're going to define our Brown-Forsythe test statistic. So the Brown-Forsythe test statistics, or BF stat, is going to be equal to the MSM divided by the MSE BF. So the MSE Brown-Forsythe. So the only difference between Brown-Forsythe test statistic is we're divided by MSEBF instead of MSEL. And this is going to be associated more approximately to a F distribution that's going to have, let's see, what is the K degrees of freedom? So K minus 1 for MSM, and then N minus K for that. So that is our BF test statistic. And it's going to be more appropriate the more farther you go from skewed. But again, we're still assuming approximately normal distributions, else this is not going to be very reliable. So let's actually compare the values of Levene and Brown-Forsythe. Right? So, because we already know that Bartlett gives us fairly different results compared to the Levene. So we know that Levene, Brown-Forsythe, and Bartlett probably will be very far from each other as well. So let's look at the MSE and the p-values for comparison, since that's what we've been looking at here. So for the MSE, for Levene, we got 161 for our data, 0.80, and then 163.11. So one could argue that, well, since the Levene and the Brown-Forsythe MSEs are close to each other, the skewness is pretty weak or pretty moderate in terms of comparisons, right? And the p-value, one can find, we found that that's 0.3040 and then 0.3020. So they're approximately equal to each other. So if you analyze skewness from the Levene and Brown-Forsythe perspective, you might argue, be like, yeah, it's a little skewed. Because, Bartlett and Levene are very far from each other, but Levene and Brown-Forsythe are close to each other, so the skewness does exist, but it's not as extreme, right? Now, that's not guaranteed, right? Our distribution, if it's not very normal, might be well behaved in terms of comparisons of Levene and Brown-Forsythe, which only difference based on the absolute difference between our values in the mean versus the values in the median. Right, but for both of these, since our p-value would be greater than our alpha value of, say, 5%, then we'd be failing to reject the null hypothesis that the variances are equal to each other, which means, at least by the Levene and Brown-Forsythe case, we have evidence to believe that these populations are homoscedastic to one another. But those are three common parametric tests, i.e. they are based heavily on normality. Variations from normality will give very misleading results for testing the homoscedasticity between two or more populations. I hope you enjoyed, and I'll see you in the next video. Take care.